Dear student, and welcome to this other edition of our function analysis class. Last time I asked you to go through the last part of the proof. Remember that we are dealing with the one norm. We wanted to show that the space of continuous function endowed with the one norm is not a Cauchy, is not a Banach space. So for that, we constructed a sequence, and we're in the process to show that it's a Cauchy sequence. So we'll go fast because we need to cover the problem so that we have a good okay. So this is where we stopped last time. But when we integrated, we found out that it's a bit different from this one. And I asked you to expand the integral that I obtained and show that when P is fixed and M goes to infinity, this norm will go to 0. And if it goes to 0, you just write the fact that the limit of this when n goes to infinity is 0, it means this. That's exactly what it means, because this goes to 0. If it goes to 0, for any sequence that converges to 0, right? Because if this is our sequence, all this, if it converges to 0, it means that the sequence itself minus 0 in absolute value, which is this again, because it's already positive, is less than epsilon. So what I mean is, if all this, we call all this because if P is fixed and n vary, m vary because you can see here, because we fixed P, m varies. So this one, we can give it a name x sub m, right? Now with this one, if we write x sub m minus a limit, which is 0 here, in absolute value, which is still absolute value of xn, but xn is positive, it's just xn. So we're saying that this minus 0 absolute value is still fn less than epsilon. So writing this less than epsilon, when it goes to infinity, that is, we can find, for any epsilon, we can find m such that when n is greater than capital N, this difference, which is this, is less than epsilon. That's exactly what we are writing here. So, and at the same time, this shows us directly that this is a Cauchy sequence. And the next thing is to show that it does not converge. And it's so easy to show that it does not converge. I hope you read it and you understood what should be done. I said that if it's not continuous at a single point of the interval 0, 1, then it's not continuous. And therefore, the sequence is not a Cauchy sequence. So if we take that same sequence, we integrate from 0 to 1/2, and then from 1/2 plus epsilon to 1. You see that for this one, if we take the limit, it goes to 0, right? When n goes to infinity. And similarly, if we take this part, this will go to 0 when when n goes to infinity. And the limit itself now, the limit h of x we are here. H of x is 1, right? Our limit. And h of x is 1 in this interval. You can see here. Because from the this norm, you can see here that this norm goes to 0. And if you integrate on this interval, it is less than this norm which goes to 0. So meaning that the integral itself is 0. If the integral is 0, the integrand is 0 because it's a positive function. So h of x will be 1 on that interval, and that's what we have here. This is for x or on that interval. For x in this interval, so for x here or on this interval, and for epsilon, positive and less than 1/2. So that's what we have. So because that is true for any epsilon less than 1 and positive, so we can take epsilon to tend towards 0. Therefore, on the interval 1/2 1, h is 1. Right. So h will be 1 there. So on one part of the interval, you have 1. That is from 1/2 to 1. That is this part of the interval. You have this one. You have 1 here, and this other part you have 0. So there's a jump there at x is equal to 1/2. So what does that mean? It means that the function is not continuous here because it's a jump from here to 1. Because to be continuous, you don't need to have a jump like this. So it's not continuous at this point. Therefore, it's not the space endowed with the 1 norm is not a Cauchy sequence. So I hope you read as I advise you to do, because this other part you can read through. I will go straight to the linear operator. This is very important, and that's what we'll be doing during the course of this week. Because in your comprehensive tests, you need to do something on linear operators. So today, tomorrow, again, and on Friday, please don't do. I expected you to come on Friday last week, but you did not show up. So we missed a practical session already, a tutorial session. So anyway, I will try to have some tutorial session online, but I advise you to come on Friday. Okay, a linear operator from from two norm spaces from x to y is what you know from linear algebra, what you call a linear mapping. Just a linear mapping between two norm spaces. And you can write it this way. You can see that it's linear. Because if you recall with linearity, there are two steps. You can show that the function, that is t x plus y is equal to t x plus ty, and then t alpha x equal to alpha tx. You can write this. Obviously, I didn't put a parenthesis here, right? It's not necessary. You can apply directly. Or if you want to put a parenthesis. Or you can combine these two in one. And that's what I did here. I combined the two in one. So these two are equivalent to this single one. Right. Okay, now, the set of all x for which tx is defined is the domain, exactly like the domain of a function, and the domain of a linear operator is denoted by dt. All right. The kernel from the real analysis, linear algebra, we have the definition, is a set of elements of the domain such that the image of that element is zero, the zero vector. And similarly for the range, the definition is similar. Now, when is a linear operator bounded? A linear operator is said to be bounded if we can find a positive case such that, because we are in norm spaces, right? X is a norm space, Y is a norm space, as mentioned here above, two norm spaces. So if I take the norm of this, I can take the norm because this is an element of Y. It has a norm. So I can apply the norm here. X is an element of X. I know the norm of X. Now, if the norm of the image of X is less than a positive constant times the norm of X, for any X, it should not be for some, but for all X in the range, if you want. If this is true, we say that the linear operator is bounded. Bounded or continuous, right? It's the same thing. Because this also means that it's continuous at zero, right? If you write the definition of continuity at zero, you see that it will reduce to this one, right? Between two norm spaces. It will reduce to this one. And we note that if a linear mapping is continuous at zero, it is continuous at any point of the space. So that's why it is enough to prove this, to call it bounded or continuous. Okay. Now, we can define the norm of that operator, not more the norm of an element, but the norm of the operator itself. Because remember that here, norm of X is the norm of an element of X that is in the domain. And Tx, the norm of Tx is the norm of an element in the range. So these are norms of element of the norm spaces. But now we are defining the norm of an operator, which is completely different. Norm of an operator. Right. Okay, so the norm of an operator, remember that we said that it's bounded. Of course, here we say the norm of bounded, right? We define only the norm of a bounded operator. It's only when the operator is bounded that we can talk about this norm, right? Because this is bounded, we know that such a positive k exists, right? But this k is not the only one, because see, if for any x, Tx, the norm of Tx is less than k, norm of x, if I take any positive number greater than k, this will still be true, right? So if it is true, it means that the infimum of this exists. It's non-empty because T is bounded. If it's bounded, it means that there is at least one positive k such that this is true. So it's non-empty. It is non-empty and it is bounded from below. It is bounded from below, therefore the infimum exists. In that infimum of such k, because we take the infimum on all the k's that satisfy this, right? The infimum of that is what we call the norm of T. The norm of T is the infimum of k's for which this relation that defines a bounded linear operator is satisfied, right? So that this condition is satisfied. So if we take the infimum of that, you know that all the elements here are positive. If they are positive, it means that the norm also is positive, right? Or zero. Positive of zero, because we take the infimum of all k positive, right? So it is positive. That norm is positive. It satisfies already the condition of the norm. When you say that the norm should be positive, that condition already is satisfied. But actually, it's a norm, right? It is a norm we can take the space of all bounded linear operator and take the operator norm. It will be also a norm space, but we'll see that later on. Now, this is the definition, right? We define the norm of the operator T by this. But now we have a proposition that gives us many other ways to define the norm. This is by definition, but this same norm is the supremum of the norm of Tx such that the norm of x is less than 1, and the other one is such that the norm is equal to 1, and the other one is the sup of these ratios such that x is not 0. So you see that we have 1, 2, 3 plus d. We have 4 equivalent definition that we can use for the norm of a bounded linear operator. Bounded linear. If the operator is not bounded, you cannot do this. You have to be bounded for this to exist, for this infimum to exist, and therefore we have this proposition. Okay. Okay, so this is another theorem. An operator is bounded if and only if it is continuous. I will record another video where I will show this, or we will do that in a tutorial. That's why I mentioned before that this definition is the same as continuity at 0. So bounded operator and continuous operator are exactly the same. Okay, now these are some examples of bounded linear operators. Okay, so I think we'll stop here and we'll continue with unbounded operator. So these are the two examples. We have the first example here. X is L1. Now you know what is L1 because we did the L1, right? Okay, this one I wrote that last year, I think so. I say read about, but with you at least I went to the LP spaces, the capital L and the cursive LP. Right. So X is L1 and Y is L infinity. Now we define this GT, which is called a modifier, right? And this is its graph. The graph of this function GT. This is the graph. It is 0 for X. Okay, here. This is -1 and this is 1. So from -1 to -infinity, from 1 to infinity, it's 0. And inside the closed interval, I mean the open interval -1, 1, the value is this. You see that this is actually it has it's a bell. It's a bell-shaped function. It's a Gaussian one. That's the shape. Now we will use this GT, which is a C infinity function, meaning that you can differentiate it infinitely many times. Remember the definition of CK. When you say that a function is CK, it means that it is continuously differentiable up to the k order. That is, you differentiate first time onto the kth time, and each derivative is continuous. Now, if you take, if it is true for any k, that is, if k is 1, 2, 3, 4, 1 billion, 3 billion, any possible value of k, natural number, you say that it is C infinity. That's very important. So it's C infinity. Now, with this G, we construct this. This is by definition, we construct F star G of X. we call this a convolution product, right? When we convolve f and g, this is called the convolution product. And the function f defined this way is called the convolution operator. So to define the convolution operator for our case, we use a function that is C infinity. And when it is C infinity, what is the result of that? You see that f is only C, is LP. So I take an LP function, f is taken in x, which is LP, where p is 1. So I take f in L1, right? And L1 functions are not necessarily continuous. They're just integrable, right? L1 means that it is integrable. A function can have a jump, but it's integrable. Might not be continuous, but still integrable. Now I take an L1 function which is just integrable. I take the convolution with a function that is C infinity. Now the result is that here, the convolution of f and g give us L infinity. L infinity is a set of function that is of measurable function, of course, because these are LP, right? LP, but P is infinity. When P becomes infinity, you call that, because remember that with P, you take the supremum, right? It means that it's essentially bounded, In other words, it gives us a function that is bounded. That has very good properties, if you can put it that way. It's bounded. So we can take the supremum of that. That's what it means. So, and this is how we define the convolution of f and g. Is defined by this integral, right? G x minus y times f of y dy over the whole real line. See, integrate from negative infinity to infinity. Okay. So now to prove that it is bounded, first of all, you show that it's linear, which is easy to show. But we only concentrate on this definition, right? This definition of boundedness. That is, if I take the norm of Tx, there is a case such that that norm is less than or equal to k into the norm of x. But in our case, our capital T becomes our capital F, because we define what we define here. We define capital F. Here, this is capital F. Yeah, sorry. Sorry, okay, sorry, I meant to. So I was saying that in our case, in the definition, we use capital T. So our capital T becomes capital F. And then our X, because we apply capital T to X, remember, this is what we had. We apply T to X, right? Now, our capital T will become F. And this X will become, because we apply it to F, you see, we apply it to F. So what we will define will be f of f like this. But when we apply f of f, it takes us to y, because this is an element of y. Now, if I'm in y, what is the definition of y? Y is L infinity, meaning that this is a function that are essentially bounded. So it is a function. So I can apply t of f of f, capital F of lowercase f, I can apply it to a point because it's a function. I can apply it to an element of R because it will take its value into R. So I take x in R. So I would need to take an x here in R, and then I apply this to that. Okay, let's say that this f of f, I call it capital G, right? Capital G belongs to L infinity of R, meaning that I need an element of R, which is a point. I need x in R, to which I apply G, right? Apply G to that point of R, because it is a function. So when I take G of x, which is this one, G of x is a function and it's defined by this, right? So it is an integral, it's this integral. Now I take the norm in the range, because in the range, I take the norm of L infinity. I have to show that it's less than or equal to a constant times the norm of what? Of f, because f is taken in x. This is f. F is taken in x. So I have to show that. And if you go through, you start from here, we take absolute value, we have this. We have that, we use the definition of the maximum norm, we take it out, and therefore we reach here. Right? Once we are there, what is the next step? We take the supremum of that. We take the supremum on x. If you take the supremum on x, this does not depend on x, so it will be less than or equal. Right? Because this is equal to that. Then I take the supremum on x, because if I take the supremum, I will recover the infinity norm of that, which will still be less than that. Now you can see that this is like my tx, and this is the norm of x. Whatever constant is there is my k. So you can see that here, k is equal to this norm of g, infinity, and this is positive. Because this g is not zero, you can see that g is non-zero, it's here. Right? Okay, but I will record another video where I will go step by step and explain that. So, and it's similarly for this second one, it is something similar. So I will stop here for today. I will come back to that tomorrow, and I will do the derivation. This is just to keep you awakened. And please read and go through the tutorial that I uploaded last time. Thank you for your time and your kind attention. God bless you and see you next time. Bye-bye.